This meeting is being recorded.
In this video from chapter 16 on acid-base equilibria, we're going to begin where we left off at the end of sample exercise 10 here. So we solved for the equilibrium constant, the Ka value of formic acid. We can also do something called calculating the percent ionization, finding out exactly how much of our acid turned into ions. So the formula for this would be percent ionization. This is going to be equal to the concentration of our product, right, of our aqueous hydronium ions at equilibrium divided by our weak acid concentration initially. So how much do we start with? And then here again, that's the equilibrium value. So we plug in these concentrations, multiply by 100, and then we would get our percent ionization. So let's use the example above. So we know that our X value, so our hydronium ion concentration was 0.0042. As we see right here above, we solve for X. We're going to divide by the 0.100 in our initial, multiply by 100, and we see that we would get a 4.2% ionization. In general, if your X is less than 5%, this approximation is fine. So you can check your work and calculate the percent ionization at the end. So again, if you're less than this 5%, you're okay to continue and just approximate. If not, we're going to see in the next example here that we have to use what's called the quadratic equation. So let's take a look at practice problem, sample problem 11 here. So we're asked to calculate the pH of a 0.3 molar solution of acetic acid. That's the chemical formula here. So let's write this down. We know that this was added to liquid water in order to get acetate ions and our hydronium ions at equilibrium. So we're told here that we have a Ka value of 1.8 to the negative 5. We have a pH. So we know that we can solve for our X value here, like we did in previous example. So let's plug in our initial, our change, and then our equilibrium concentrations here. We always just cancel out the water because we know that liquid water doesn't actually change concentration. So let's see, we're given 0.30 as our initial here, and we assume that we have none to start with. Due to the balanced chemical equation, we're going to say that for every 1 mole of acetic acid that we lose, so negative 1x, we gain plus x over here, 1 mole of each of these ions. Then we have our equilibrium would be 0.3 minus x, 0.30, and then x and x for our two products. So like we've done in the past, we can set our Ka value, our equilibrium constant, equal to our products over our reactant. And we don't have information to solve for X or to plug in to X here. So we have to actually use our Ka value to solve. So I'm going to rearrange this. I'm going to multiply both sides by 0.30 minus X. So that will cancel out over here. And this would look like 0.3 times, we'll approximate, right? We'll keep that X for now, 1.8 times 10 to the negative fifth. We'll assume that this ionizes actually less than 5%. So we're going to take away that, that X because we were told earlier if we're less than 5% ionization, it's okay to assume that that X disappears. So let's see if we can get through this without using the quadratic formula. So we have 0.3 times 1.8 to the negative fifth equals x squared. We can take the square root of both sides. So we'll multiply these two terms together and then take the square root. That will give us our x value. And we can solve for x then. So that would be, again, 0.3 times 1.8 to the negative 5. When you take the square root, you get about 0.0023 for your x. This is equal to our hydronium ion concentration. So I was excited. I thought we would do a quadratic here, but it looks like we don't have to, because if we check our percent ionization, we'll see that 0.0023 ionized. We divide that by our initial concentration, multiply by 100, and we're going to get this very small percent ionization. So our approximation of that initial concentration of 0.3 is just fine for this problem. So we have one last step. We have to solve for pH. So now that we know our approximation is good, pH will be the negative log of 0.0023. And that gives us a pH of 2.63. And that looks good because we know that this is about 2.3 times 10 to the negative 3. So this looks like a reasonable pH for this solution of acetic acid.